Students, today we are going to study about electromagnetic theory of light. The phenomena like interference and diffraction in optics fully supports the wave theory of light formulated by Christian Huygens. At that time it was believed that for the propagation of light, there requires a media, and it was believed to be the existence of ether media. You know about ether media. It is in the form of fluid, maybe gas or liquid. But in this media, only longitudinal waves can propagate. Hence, it was believed that light was a longitudinal wave. But after the discovery of polarization of light, that is by scientist Fresnel, which suggested that light waves are transverse, and the propagation of these transverse waves, there needs a elastic media, maybe elastic solid media, and due to this the existence of ether media was discarded because the ether media obstructs transverse waves. At this juncture, scientist James Clerk Maxwell, who lived in the year 1831 to 1879, he put forward a theory known as electromagnetic theory of light, which removed the difficulty of this wave theory. According to James Clerk Maxwell, light is an electromagnetic wave, a source of light which produces periodic variations of electric and magnetic fields in the surrounding space, and these variations have all the characteristics of transverse wave. Zeeman effect, Faraday effect, it showed that there is a close relationship between light and electromagnetic phenomena. This was proved experimentally by one more scientist, that is Hertz, in 1888 by producing electromagnetic waves using an oscillatory circuit. These electromagnetic waves have all the properties of light like reflection, refraction, diffraction, etc. Hence, light waves are nothing but electromagnetic disturbance propagated in the form of waves. Here in the electromagnetic theory, James Clerk Maxwell, he has put forward a 4 equations, and these 4 equations means it was explained mathematically by James Clerk Maxwell by 4 equations. They are, first one, Maxwell's equation, which represents Gauss law in the mathematical form and which describes the relationship between charges and electric fields. Second equation is for magnetic fields, and it explains the absence of magnetic monopoles. Third equation is Faraday's law of electromagnetic induction, and the fourth equation is known as Ampere's circuital law, represented in mathematical form. First, now let us see James Clerk Maxwell has given this equation of electromagnetic theory in dielectric media. First, let us see about this. So, I am given the heading as polarization of dielectric materials. So, what are these dielectric materials? They are nothing but insulators. But in this insulator, we can establish an electric field. An ideal dielectric is one which is devoid of free electrons, means there is no free electrons. And the molecules of dielectrics, they are mainly classified into two types. They are polar molecules and non-polar molecules. So in case of polar molecule, the center of positive and negative charges, they are separate. They do not coincide. Even in the absence of an external electric field, here you have to consider electric field, it acts as an electric dipole. Dipole means which has two polarity, that is plus and minus, which means that charges are separated with a distance. But the dipoles, they have random orientation, means their orientations are different. Hence, the net dipole moment is 0. This is due to the random orientation of molecules. That I can explain here. In case of, let us consider a water molecule or HCl molecule or carbon dioxide molecule. These are all the examples for polar dielectric materials. Now let us consider HCl molecule. In this, hydrogen is positive, means it has a positive charge, and chlorine which has negative charge. And the distance between these two charges is taken as R. Then dipole moment P is given by the product of charge and the distance between them, that is P is equal to Q into R. And this dipole moment is always having a direction from negative to positive side. So when an electric field is applied, what happens to these dipoles? They will tend to align themselves in the direction of the field, and the dielectric takes on an orientational polarization. In case of non-polar molecule, the center of positive and negative charges coincides. Hence, the dipole moment is 0 in case of non-polar molecule. But when an external electric field is applied to this non-polar molecule, the negative charge in it gets slightly displaced in a direction opposite to the electric field applied to it. The dielectric is then said to be polarized. A polarized dielectric acquires surface charges which contributes to the extra electric field. So here you can see the figure. These are all the dipoles in which you are having positive and negative charge, which are separated by a small distance, and this will give rise to a dipole moment. But if you see other molecules of the same material, their orientations are different. Here the moment is in this direction, here it will be in this direction. Hence net dipole moments gets cancelled, it becomes 0 due to the different orientation of these dipoles. This happens in case of dielectric material when there is no external electric field is applied or there is no external electric field. Now for this dielectric material, where the orientation of these dipoles are different, if we apply an electric field, what happens? Let us see here in this figure. These dipoles, they gets oriented with the applied electric field. So the direction of this orientation of these molecules which are in the different direction, they gets oriented with the direction of the electric field, and this gives rise to net dipole moment. So this is already I said. If R represents the displacement of the negative charge with respect to the positive charge that I explained earlier here. So if I'll consider positive and negative charge with the distance R, then the dipole moment, which is represented by the vector P, which is equal to the product of charge and the displacement between the charges, Q into R. If we consider unit volume of a substance, means dielectric material, then there will be n number of dipoles. And if we consider volume V, if there are n number of dipoles that we are considering in volume V, then what is the dipole moment per unit volume is given by n is the number of dipoles in the volume V. Then how many number of dipoles are there in unit volume is nothing but n by V. Then what is the dipole moment? Each dipole will give rise to a dipole moment of Q into R. Then the dipole moment due to n number of dipoles in unit volume is P is equal to n by V into Q into R. So this is the dipole moment in unit volume of the dielectric material. So this again I have explained here. This is the separation between the charges minus Q and plus Q of a dipole, that is given by R. Then dipole moment is given by P is equal to Q into R. So this dipole moment per unit volume is called the polarization or polarization vector P of a material. It was found that this polarization P is directly proportional to the applied electric field. Why? Because this polarization has occurred due to the applied electric field, the orientation of molecules which took place after the application of electric field. Hence, whatever polarization occurs in case of dielectric material is directly proportional to the applied electric field, or P is equal to polarization P is equal to epsilon naught into chi into E, where epsilon naught is called as permittivity of free space or vacuum and chi is called electric susceptibility. Now I am going to explain an equation known as equation of continuity. It is also known as continuity of current equation. So here I have given the explanation. According to the law of conservation of charges, the total charge contained in an isolated system remains constant. Or you can say charges neither be created nor be destroyed in an isolated system. It is also known as law of conservation of charges. Or you can say in an isolated system means where there is no external forces acting, then whatever the charges inside that isolated system remains constant. It will not vary. And that is known as law of conservation of charges. And this is expressed in the form of an equation called as equation of continuity. So we are going to explain the law of conservation of charges in the form of an equation known as equation of continuity. So this is how we are going to prove. Let V be the velocity of the charge at a point where the charge density is rho. Rho means number of charges in that particular area, rho. Then the charges passing through unit area in unit time is called current density. Usually you write current density J is equal to N E into V, where N is number of charges, E is the charge and V is the velocity of that charge. But here we have written this current density in terms of charge density, where charge density is rho and V is the velocity of those charges. Then the current I emerging from a normal surface S is given by I is equal to the surface integral of J ds. You know, current is nothing but flow of charges. Then charge passing through unit area in unit time is called current density, that is J, which is equal to rho into V, where rho is not a vector, so this should come outside, it's not a vector, and V is the vector. So see here, this is rho into V, where V is the vector. V is velocity. Number of charges passing through or emerging from a normal surface is nothing but current, and it can be expressed in terms of surface integral, and it is and the surface is considered as a closed surface, and that is taken as the surface integral of J ds. So why we are taking the integration? Because a small change in the current di, if I consider, then di is equal to J into ds. It is the small amount of current in a surface ds. Then how to find out the total current in surface S? That is by integrating. So integration implies the total current which is passing through a surface S. So this equation I is equal to surface integral of J ds, which implies the total current passing through the surface S. So this is considered as equation 1. And when current is emerging from a surface, then there will be decrease of charge in that particular surface. So this is expressed as, this must be equal to the decrease of charge in unit time inside the volume V, which is bounded by the surface S. So we are considering the same surface S, and we are going to write current in terms of charge. So you know that current is nothing but flow of charges. So when current is emerging, there will be decrease of charges with respect to time. Hence, I is equal to delta Q by delta T. But what is Q? Q is nothing but, it is the volume integral of rho dV. Q is equal to volume integral of rho dV, nothing but number of charges which are there in the volume dV is nothing but dQ. Then total number of charges in volume V, which is bounded by the surface S, is given by, you are adding all the charges in the small volumes of dV. Instead of that, you are doing integration. What type of integration you have to take? Volume integration, because charges are there inside the volume V, which is bounded by the surface S, means through that surface current is emerging. Hence Q is equal to volume integral of rho dV. Now you are going to substitute this Q in this equation, that is I is equal to delta Q by delta T. Then I is equal to minus, why negative sign? Because the charges are decreasing, hence we are using negative sign, minus volume integral of delta Q by delta T into dV. Here instead of Q you are writing this. This is equation 2. From equation 1 and 2. So what is equation 1? That is equation which is related to current, I. What is equation 2? That is also a equation related to current. Hence these two equations represents the same, that is nothing but current, and hence they should be equal. That's what we are writing here. From equations 1 and 2, we have surface integral of J ds is equal to minus volume integral of delta Q by delta T into dV. Now you already studied the Gauss divergence theorem. From Gauss divergence theorem, we can write surface integral in terms of volume integral. How? If we'll consider surface integral of vector field, that is as J, then it is equal to volume integral of divergence of that vector field, that is J dV. This is how we are writing or equating the surface integral and volume integral. By using this Gauss divergence theorem, volume integral of divergence of J dV is equal to minus volume integral of delta Q by delta T dV. So this you are going to write here. So you are replacing surface integral of J ds by this. Or now here both side you are having volume integral. So when you are having same integral, get the terms in one side. You can take the total integral of those two terms. Then you can write the integrand as div j plus delta q by delta t, and you are taking the volume integral. So volume integral of divergence of j plus delta q by delta t dv is equal to 0. Since the volume over which the integration performed is arbitrary, the integrand of the above equation must vanish. What is the meaning of it? The integration of this integrand is equal to 0, which implies that integrand should be equal to 0. Hence, we are writing it as divergence of j is plus delta q by delta t is equal to 0, or divergence of j is equal to minus delta q by delta t. So, you know divergence means, that is, in case of fluid, if I will consider, the divergence means this what we can flux of that vector field which are moving away from the point. Then here it is given as divergence of j, divergence of current density, which means the charges are moving away from that point. Hence, the charges are decreasing. So, hence we can write del dot j, or divergence of j, is equal to minus delta q by delta t, and this is known as the equation of continuity. So here I will stop the class. In the next class, let us see the Maxwell's 4 equations.